Okay, hold on. We had a few technical difficulties. So here's the drawing. We had to restart it. So we had three carbons, and they have 4 valence electrons, 6 hydrogens, they have 1 valence electron, and 1 oxygen with 6. So that means we had 12 electron pairs. And so when you drew the propanol molecule, I'll redraw it for you. I will do that. Okay. You should have drawn the carbon-to-carbon bonds. They showed you that they wanted the CH3s on the end with the way they wrote out the molecule. And then once you drew it out, you should have gotten a double bond on the oxygen with those 2 lone pairs. So that's for 1. Then it asks you to predict the carbon-to-carbon-to-carbon bond angle. So that means I only had to look at my middle carbon and say, what is the angle going to be here? So I notice how many things are bonded to my central carbon?
3.
3. Okay, I've got a carbon, an oxygen, and a carbon bonded to the central one. Are there any lone pairs on the central carbon?
No.
No. Okay, so what shape is this? Trigonal planar. Okay. What is the bond angle in a trigonal planar molecule?
120.
120 degrees. So I know the carbon-to-carbon-to-carbon bond angle is going to be 120.
Absolutely.
Okay. All right, then you'll notice I skipped B and C. That's because that's material that goes with the next unit that the AP people had just included in one exam question. So we'll probably do that one next unit so you can see how they would put it together. D says, given the structural formula for propyne below, indicate the hybridization of the carbon atom indicated by the arrow in the structure above. So we're looking at this carbon here. How many areas of electron density surround that carbon?
2.
2. Okay, remember, this triple bond just counts as 1 area of electron density, right? It's 1 clump of electrons, and then we've got that one right there. So 2 areas of electron density. So what hybridization is that going to be?
You got SP.
SP. So your hybridization there should be SP. Does everybody see that?
Yes.
All right, and then the second thing it asks you to do is it wants you to indicate the total number of sigma bonds and the total number of pi bonds in the molecule. Okay? Now, single bonds are always just what?
Sigma.
Sigma. So let's take a few notes here before we do this. Single bonds are only sigma. Okay? Double bonds are what?
Sigma pi.
1 sigma, 1 pi. And triple bonds are
Sigma pi pi.
2 pi.
sigma, 2 pi's.
Pi pi.
Okay? So, how many sigma bonds do I have in this molecule? I've got 1, 2, 3, 4, 5, and then I have what? 1 with the triple bond.
Okay.
So I've got 6 sigma bonds. And how many pi bonds?
2.
2 pi's from that triple bond.
So, like, so we got 2. When it, like, what? How is sigma and pi bond? How is that useful? I'll be honest. Like, how is it like? Would you use it like, you know, this sigma represents something on the test or something?
Would you ever like explain?
You're never going to have to use it to explain something. That's pretty much the extent of what they would ask you about sigma and pi bonds on the AP exam. It's how many sigmas, how many pi, or, you know, what kind of bond is represented here. Really, as far as you are concerned, it doesn't really help your life to know sigma and pi. But as far as scientists are concerned, it helps them to figure out how these things are bonded together, which then helps us know like what properties they're gonna have. Something as simple as, is it going to be a gas, liquid, or solid at room temperature? You know, how is it going to bond with something else? How is it going to interact with this molecule? If I mix it with this, how is it going to react? We can get a lot of that by looking at how it's bonded, which would be like if you get into like biochemical stuff and all that. So, okay. All right, 1999. Says, answer the following question using principles of chemical bonding and molecular structure. A says, consider the carbon dioxide molecule and the carbonate ion. The first thing it wants us to do is draw the complete Lewis electron dot structure for each species. So let's start with CO2.
So C,
Carbon has how many valence electrons?
it's got 4,
4. Oxygen has
6,
6, and I'm going to multiply that by 2. So 4 plus 12 is
16,
16, divided by 2 is
8.
8. So I know I need 8 pairs of electrons. So, let's start my drawing. I put carbon in the middle. I show my oxygens on the outside. And I make sure everything obeys the octet rule.
Nope.
And then I count.
Double
And I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Why would you put,
You need to
Long
put
hairs
2
on
double
carbon.
bonds on it.
Okay? Huh?
you can't put 2 pairs on the
Why did I put the long hairs on carbon?
Yeah, like-
Because carbon has to have 4. Has to. It will be satisfied with less than 4. So I have to put either lone pairs there or I've got a double bond there. And when I put the lone pairs, I realized I've got what?
2 bonds.
Too many bonds. So that means I need to change these lone pairs to what?
Double bonds.
Double bonds. So now I've got 1, 2, 3, 4, 5, 6, 7, 8. Notice oxygen has how many surrounding it?
4.
It's got 4 pairs. That's what it wants. Carbon has how many? 4 pairs. And the oxygen on the end has 4 pairs. So is everybody happy? Everybody's happy.
How would you draw that in the other thing? Would you just draw a line, or can you not do that?
Yes. No, you wouldn't be able to do it.
Okay, so it has to be at least 2 carbons.
Because if you draw a line with the other thing, then you're assuming there's a carbon there and a carbon
That's
there.
what I figured.
All right. And then we draw the CO3 to negative. So carbon has 4, oxygen has 6 times 3, and then I have to add 2 because there's a negative charge there. So 4 plus 18 is 22, plus 2 is 24. I divide that by 2 and I get 12. So I put my carbon in the middle. I show all of my oxygens. Actually, let me draw this. What's the problem with this drawing?
It's not a very offset.
Carbon doesn't have 4, and if I add a lone pair, what have I done?
You got too many.
I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what do I need to do?
Make a double bond.
I need to make a double bond. How many double bonds?
2.
You
Just
make,
getting 1.
you can
Just 1, right? Because I only had 1 too many pairs, so that means I just need to make 1 a double bond. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
You have to draw the other one, the other version. Of
And
it.
then I'm going to put this in what? Brackets. Actually, when I pulled up the way they scored this on the AP exam in 1999, they put in parentheses, resonance structures are not needed for this question. So they were okay if you did not give the resonance structures. My only thing is it'll take you 2 extra minutes to swap around some double bonds, and what if they wanted it? Do you really want to miss out on a point just because you wouldn't move the double bond around a couple times and draw a couple extra molecules? So I would probably draw them. But for now, we're just going to pretend like we drew the other resonance structures. Okay. All right. So now we've got those drawn. B says account for the fact that the carbon-oxygen bond length, notice we're talking about the bond length, okay? Because we automatically start thinking about bond what? Angles, right? We're thinking bond angles. They're asking about bond length. Why is the carbon-oxygen bond length, let's just pretend like we're talking about this one. Because remember, if we draw the resonance structures, the double bond can be anywhere. And that's because we're showing, is there really a greater density in one area than the other? No, the electrons spread out evenly. So why is the bond length for this one, for my CO3, greater than the bond length here? There you go. A double bond causes the bond length to do what? the bond length decreases. Why does the bond length decrease when I have a double bond?
Because you're
Okay, because I have greater what?
Greater
electrode, just
Greater electron density. Okay, I've got more electrons here in this double bond, so it causes these positive nuclei to do what?
attract.
To move closer. And I did it like this earlier. Imagine I've got a positive here and a positive here. And then I've got another positive here and another positive here. I put 4 negatives, I put 2 negatives. Which one are the positives going to move closer to?
Before.
The 4 negatives, right? So these are going to move in closer than these at the bottom are. Does that make sense? Sorry, Hope. Do we understand that? That's how the electron density causes the bond length to shorten. B says consider the molecules CF4 and SF4. 1 says draw the complete Lewis electron dot structure for each molecule. So I'm going to clear the ink and we're going to start this all over again. So carbon has 4 valence electrons, fluorine has 7, multiply that times 4. 4 plus 28 is 32, divided by 2 is 16. So I'm going to have my carbon in the middle, 2 more fluorine, 2 more fluorine, 2 more fluorine. Here's the good news about this question here, if they were to give you something like this again, you all know how to draw them. Okay? So even if you can't answer the questions about them, you should at least be able to get 1 point apiece for the drawings. So for this question, that would have been 4 points already, because we've already drawn 4 things. Yay?
Out of how
We
many?
can do this.
8 or 10.
Yeah, so you're shooting for about half, so you want about 4 or 5.
I got this.
You got this. Then SF4, sulfur has 6 valence electrons. Fluorine has 7, so 6 plus 28 would be 34 divided by 2. So for this one, I need 17 pairs. So I'm going to draw it the same way again. Except this time, since I need an extra pair, the extra pair has to go where?
Sulfur.
On sulfur. So sulfur has a lone pair. So then the last question is, in terms of molecular geometry, account for the fact that the CF4 molecule is nonpolar, so this is nonpolar, whereas the SF4 molecule is polar. So let's pretend for a second we're on the AP exam and we don't know anything about this question, but I look at the 2 drawings, and what is literally the only thing that is different about them?
Sulfur has an extra pair.
Here you go, this extra pair of electrons, that lone pair, right? So that lone pair is somehow affecting the polarity, correct? Now remember, we said if the charge is evenly distributed, what happens to the polarity of the molecule? It goes away, right? Alright, just goes away. Do you agree?
Yes.
Right. So, here on the carbon, what shape is this molecule?
Trigonal or
Tetrahedral.
That's what I was going to say.
It's okay.
I was wrong.
Alright, so that means all of these fluorine are exactly how many degrees apart?
145.
109.5. So is the charge completely spaced out evenly?
Yes.
Yes. What happened when I added this lone pair over here with the sulfur?
You make
Push
it
it
four
away.
by
Push some more around.
There you go. It's going to cause these fluorines to be pushed and bent. So is this molecule going to have an even distribution of charge?
Yeah.
No. So you would say the lone pair in sulfur causes the charge to be distributed unevenly. I know I'm writing sloppy. I'm trying to write low.
It's okay. I understand.
So it is polar. Another way that they like for you to explain it is if you look at the CF4 molecule, y'all remember when we drew them 3D? Okay, if I cut this in half, it would be completely what? Symmetrical. That's when you know that the charge will cancel. Okay, because if I cut it in half, it would be symmetrical. Okay, because of this long pair, if I cut this in half, it wouldn't be symmetrical. So if you want to make it real easy to answer these questions, you could just say the SF4 molecule is asymmetrical because of the long pair, making it polar.
Think we're done?
Questions, comments, concerns?
Ah.
All right, we're done.
Yes, ma'am.